So, hi guys, this is Prasoon Varshney. This is Study with Sam series. Let me introduce myself first. Okay, I'm Prasoon Varshney. I'm a learner, hustler, and explorer. Uh, and actually, let me say this line. Okay. So, anyone says, introduce yourself. So, what do you do? So, I'm Prasoon Varshney. And I'm a learner, hustler, and explorer. I love to explore things, and basically, friends call me as a creative and logical analyzer who can be trusted, come up with new ideas, solutions. I'm I'm actually okay. What I will, I'm a quick learner who is eager to learn new things. Basically, so you can say that. So I'm a self learner. Okay, this will work. ये तो खाया ही नहीं है भाई पेट भर रहा है यार मम्मी खिचड़ी दे के खिलाती है पड़ता खाना नहीं खा बिल्कुल भी रात को खा लेना बस ये छोड़ना मत हाँ रात को खाना ठंड पड़ रही होगा हीटर पे रहते हैं हाँ ये तो छोड़ना मत हाँ छोड़ूंगा नहीं रात को भूख लगेगी जल्दी So basically, what I was saying, I'm a quick learner who is always eager to learn new things. You can add this thing in introduction, your introduction. So basically, let me sum up my introduction again. Hi guys, this is Prasoon Varshney. I am a quick learner. I'm a learner, explorer, and hustler. Actually, I'm a quick learner who is you can say I'm a quick learner who is always I'm a hustler and I'm a quick learner. I'm a hustler and a quick learner who is always eager to learn new things. You can say that also. What I'm trying to say that. Hi guys, this is Prasoon Varshney. Okay, basically I'm a hustler and a quick learner who is always eager to learn new things. I'm from Aligarh, Uttar Pradesh, and I am studying in NIT Kurukshetra, and the program name is Master of Pursuing Master of Computer Applications. Okay. So yeah, you can say that, and I love to teach people. Not teach people means I love to teach what just I learned. Okay, I love to do that. That's my hobby also. Okay, basically you can say that to help someone. Uh, okay, when I was in that situation, I was facing issues, and so I love to help those people who are facing that problem which I faced previously. Okay, so I love to help them also, and yeah. Okay, I'm not feeling that well actually because I don't know, I'm not feeling good. Not feeling good. Anyways, I have to study. Okay, let me. Before starting this session, let me take a casual break because I want to go washroom. Okay, so yeah, let's take a casual break. I'm just coming in 5 minutes. Okay, yeah. Okay, I'm back. Okay, I'm back. So what I was doing. Okay, let's start our session.
So I teach these subjects of microprocessors and microcontrollers, 8085, 808. I'll be making will be interrupts and that will be uploaded within a day or two. Okay, now, so let's start. You write call 2000. What is 2000? The address of the subroutine. You get hello people, I'm Bharat Acharya. To 2000 executes the subroutine. At the end, it sees return. Will it get lost? Oh my god, I have to go back, but I don't know the way. How do I go back? It knows it has stored the return address in the stack. It will simply do a pop from the stack, get back the return address, put it back into PC, and that's how it will come back to the main program. Tell me, did you understand this? So, let's take another example and do it so that we are damn sure. We are at location 6000. We want to call a subroutine at 9000. This is return. What will happen? We will write call 0090. This is your call 9000, which will be at 6000, 6001, 6002. 6003 is the return address in our context. Processor will fetch this, fetch this, fetch this. This will be held in WZ. At that point, PC is 6003. Fetching is over. Now processor knows it has to go here. So PC has to get 9000. But the moment it puts 9000 into PC, it will lose this number 6003, which it's not going to get from anywhere else after this. So before putting 9000 into, I'm going so fast because I'm just revising. Before putting 9000 into PC, first it will push the value of PC into the stack. So what number will it be storing? 6003. 6003 has been held now into the stack. Now PC will get 9000, processor will go to 9000, executed. On return, it wants back that number. It will do a pop PC from the stack. Will get back the number 9003. That is the return address. Come back over here at the 6003. I'm sorry. We'll get back the number 6003. Come back over here and continue. Please tell me, did you understand? Now, the question is, this return address was stored in the stack. Why is it stored in the stack? Of all places in the world, why is the return address stored in the stack? Because of this. This is called nested subroutines. From one subroutine you call another, from there you call another, from there you call another. That's called nesting. Nesting means one within the other. So this is a call, this is also a call, this is also a call, this is a return, so is this is also a return. Now during a call there is a push, there is a push, there is a push, there is a pop, there is a pop, there is a pop. Let's call this return address 1, return address 2, return address 3. While going to the first subroutine, processor will push return address 1 in the stack. Under normal circumstances, this subroutine would have got over. On return, processor would have done a pop, would have got back the same return address and would have come back. Now, coincidentally, during the subroutine, there is another call. Since there is another call, there has to be another push. When it does another push, it will do another push of R2. Where will R2 come? It will come above R1 because that's the second push. Now, it will push R3. While going, you have pushed R1, R2, R3. While coming back, all the three returns are going to do a pop. Will they choose and pop? Will they say, oh, this is mine, oh, that looks like mine? No, all the three returns will pop blindly. Whatever they get, they will assume it to be the return address. We have pushed them in the order R1, R2, R3. We want them back in the order R3, R2, R1. That is why return addresses are stored in the stack, because stack works in the principle last in, first out. Whatever you store, you get it back in the reverse order. And that completely plays into our hands over here. Please tell me, did you understand this? So return addresses are stored in the stack. Now, another question students ask is, during a subroutine, what if we do a push? No problem. You feel like doing a push? Go ahead. See to it that you also do a pop. Simple. During a subroutine, number of pushes should be equal to number of pops. Isn't it simple? Look at my fingers. When we enter a subroutine, right at the top of stack, the return address has been stored. By whom? By mu. Now, during the subroutine, you feel like pushing something into the stack. Go ahead, push. See to it to also do a pop. You do 2 pushes, do 2 pops. You do 3 pushes, you do 3 pops. If you do 3 pushes and 2 pops, your data is above the return address. On return, processor will do a pop. Like I said, it doesn't choose and pop. Whatever it gets, it will assume that to be the return address. So it will take this as a return address. And instead of coming back over here, it will straight to some unknown location. Whose fault is it? Yours. Yours means not rotate personally. Yours means the programmer's. So the programmer, he or she, should be aware, if you are writing a subroutine, follow this rule. During a subroutine, number of pushes should be equal to number of pops. Please, are you clear? Now,
Yes, sir.
now that you understood,
Means you want to say that if you want to push, if you want, we can, if we say, we see in the case of subroutine, you can say that the top of the stack would contains the return address. Okay, the top of the stack. Okay, my bears are. Hmm. 1 second. Where is OBS? Okay. मेरे बाइक हुआ हुआ है रो जाओ ज्यादा खा लिया क्या ओके अब तक कुछ ज्यादा खा लिया नो प्रॉब्लम so what I want to say that he's telling that if we use push and pops you if you're doing 3 push and they do also 3 pops okay
overall working, we just need to see it in steps. What are the steps? During a call, there are 1 and 2. 2 steps that happen. First step, push PC into the stack. This is the stack. This is the top of stack pointed by SP. This is SP minus 1. This is SP minus 2. This is PC, which is basically PC higher byte, PC lower byte, which in our context in this example 1003. To push this into the stack, since this is 16 bits, it will require 2 locations, so it is 2 sub operations over here. This is higher byte, this is lower byte, this is minus 1, minus 2 lower address. You know the principle, lower byte, lower address, higher byte, higher address. So PCH will be stored here, PCL will be stored here, SP will get decremented twice. So the sequence, the actual sequence, which you don't need here, you need it in timing diagrams, but since we are doing so much, I'll just tell you. The whole sequence goes like this. SP will become SP minus 1. We will put the value of PCH. SP will again become SP minus 1, which effectively means SP minus 2. and we will put the value of PCL. These are the steps of call. So let me write the steps. SP becomes SP minus 1. At the new location pointed by SP, we will put PCH. SP again becomes SP minus 1. At the new location pointed by SP, which effectively is SP minus 2 now, we will put the value of PCL. This was your first step. Second step, PC will simply get the number 2000 from WZ. This is the whole execution of call instruction. Please tell me, is this clear? Next one, return. Return is the easier instruction. The moment it is fetched, processor knows it has to return. Where does it get the return address from? Stack. So there's only one step performed over here. Pop PC from the stack. This is your moment by SP minus 1. At the new location pointed by SP, we will put PCH. SP again becomes SP minus 1. At the new location pointed by SP, which effectively is SP minus 2 now, we will put the value of PCL. This was your first step. Second step, PC will simply get the number 2000 from WZ. This is the whole execution of call instruction. Please tell me, is this clear? Next one, return. Return is the easier instruction. The moment it is fetched, processor knows it has to return. Where does it get the return address from? Stack. So there's only one step performed over here. Pop PC from the stack. This is your stack. The number in our example is 1003, which was stored in the stack. This is the top of stack. So this is SP. This is SP plus 1. This is SP plus 2. Remember, we stored 1003, right? This was 1003, which we stored as 10 and 03. And SP eventually pointed here. So that's the same picture. SP is pointing over here. SP plus 1 is 10 and SP plus 2 is some other value which is there in the stack. This is the point of interest. This is what we want. This will be popped out into PC, which is PCH and PCL. 03 will come to PCLY. Lower byte, lower address, higher byte, higher address. Same principle. That principle works everywhere. There's no contradiction to that principle. I teach 7 processors. No contradiction. Okay. So always follow the principle. This rule is called little endian rule. If you learn a processor which follows big endian rule, it will be opposite. But all the processors that most people learn, Intel processors, they all follow little endian rule. So lower byte, lower address, higher byte, higher address.
Little endian.
So PCL will get 03, PCH will get 10, and as these two are popped out, SP will come back over here. So it will get incremented twice. So the actual sequence is PCL gets this data, SP will become SP plus 1, PCH gets this data, SP becomes SP plus 1. So just like I wrote the steps over here, I'm writing the steps. First step, PCL will get the data pointed by SP, SP will then become SP plus 1, PCH will get the data pointed by SP. Once again, SP will become SP plus 1. Please tell me, did you understand? So that was your push. So indirectly, you've also learned push and pop. We were learning call and return, but you also learned push and pop instructions. Please tell me, did you understand? A call does a push, a return does a pop. Are we clear? Now, this in Bombay University is a 10-mark question. The question is either a direct question, explain call and return, or an indirect question, explain the execution of a subroutine. So all of that with all the explanation which I said should be there in your answer. Now, if you understood call instruction, you'll understand this. This is nothing else but a shortcut to do call. Call, something like call 2000 is a 3-byte instruction, 1 byte for the opcode and 2 bytes for the operand. Now, so what do you understand? Every time you want to call a subroutine, you need to use a 3-byte instruction. You understand 3-byte instruction takes 3 cycles for fetching, takes 3 locations for being stored, etc. Now, do you understand there are lots of functions which are necessary all the time? You know they are going to be called regularly, the regularly used function in any application. Like in a car music system, volume up, volume down. That's a small tiny system. So volume up, volume down is like the most regularly used feature. Track up, track down. These are the most regularly used features of a car. Now, you understand these are all functions, so they have to be called. You understand a call instruction is a 3-byte instruction. That means it's going to take 3 cycles every time. Now, you know that there are some functions which have to be called all the time. Why not just make faster calls for them? So there is a faster call instruction called RSTN. RSTN, where N can be any number from 0 to 7. RST stands for restart. This is called software interrupt. Again, the reason why I was not doing interrupts is the execution of a subroutine. So all of that with all the explanation which I said should be there in your answer. Now, if you understood call instruction, you'll understand this. This is nothing else but a shortcut to do call. Call, something like call 2000 is a 3-byte instruction, 1 byte for the opcode and 2 bytes for the operand. Now, so what do you understand? Every time you want to call a subroutine, you need to use a 3-byte instruction. You understand 3-byte instruction takes 3 cycles for fetching, takes 3 locations for being stored, etc. Now, do you understand there are lots of functions which are necessary all the time? You know they are going to be called regularly, the regularly used function in any application. Like in a car music system, volume up, volume down are a small tiny system. So volume up, volume down is like the most regularly used feature. Track up, track down. These are the most regularly used features of a car. Now, you understand these are all functions, so they have to be called. You understand a call instruction is a 3-byte instruction, that means it's going to take 3 cycles every time. Now, you know that there are some functions which have to be called all the time. Why not just make faster calls for them? So, there is a faster call instruction called RSTN. RSTN, where N can be any number from 0 to 7. RST stands for restart. This is called software interrupt. Again, the reason why I was not doing interrupts is you need to know a lot before you learn the topic of interrupts. Anyway, so they are also called software interrupts. That's just another name for them. So when you write RSTN, it's the same as writing call N into 8. So if you write RST0, it's the same as writing call 0000. RST1 is the same as writing call 0008. RST2, 0010. How do you get the number 0010? This is 8, this is also 8. You know, you understand, right? Hexadecimal numbers 0, after 0, 1, 2, 3, 4, 5, 6, 7, 8. So there's a gap of 8. Then again after 8, 9, A, B, C, D, E, F, 1, 0. So again there's a gap of 8, you reach 1, 0. Then again 8 will give you 1, 8, then 2, 0, then 2, 8, then 3, 0, then 3, 8. So what happens? Writing RST0 is the same as writing call 0000. Students say, why 2 instructions then? The difference is call 0000 is a 3-byte instruction. RST0 is a 1-byte instruction. So it does that job much faster. 1-byte instruction means 1 cycle it will be fetched. 3-byte instruction requires 3 cycles. Students say, sir, 2 cycles you saved. What big deal? Processors can do millions of cycles per second. I know they can do. But if you know there are some functions which are required regularly, then this will be multiplied with the number of times you are using that function. Some functions are required all the time in any system. Like I give you a simple example. Volume up, volume down, your remote control. Your remote control doesn't work by magic. There's a processor inside. It's a microcontroller, but basically there's a processor inside. So even in that, there are some functions which you need all the time. So for them to be executed the fastest, yeah, you press some random button in your remote control which you use very rarely. If there is a lag for it to open, you don't mind because you know you use it very rarely. But things which you use on a day-to-day basis, they should work as fast as possible. So for that, they've created this small RSTN instruction which works the same as call. The only difference is instead of 3 bytes, it's 1 byte. So there's a function stored at 0000. You want to invoke it, you have 2 options. You either use call 0000 or you use RST0. RST0 is the faster one. But it will not work for every location. These are the stipulated locations for which the RSTN instruction works. The working is the same as call. Okay, that's it. Those are all the branch instructions. I hope you enjoyed learning it. I think call is a very interesting instruction to learn. If you understood this, you'll understand the timing diagram of call very easily. It's a 3-byte instruction, opcode fetch, memory read for fetching, and 2 memory writes, because you can see there are 2 writes happening in the memory. One is SP-1, the other is SP-2. So opcode fetch 60 states, 2 memory reads, 2 memory writes, 6 plus 3 plus 3 plus 3 plus 3 plus 3, 18 T states. Anyways, I'll be doing a video on timing diagrams later whenever I can. I'm covering up all the important topics first. Processes are very big. There is so much to learn. Students every day, a lot of love shown by students by just sending requests, so please make a video for this, etc. But being a teacher, knowing what videos to shoot first is a call that I'm taking from an experience of teaching this subject for so many years. If I do a stepper motor video, yes, what do you learn from it? Only a stepper motor. If I do instructions and programs, what you learn from it is how to write programs for everything. So I'm just doing all the important topics first, but eventually there will be videos for every topic. Sometime in life, all of them will be covered. We're shooting every day as fast as we can. Okay, all the best, do well.
Okay, sir. मिटा क्या A program sequence is transferred to the memory location specified by the system there and given number because before the transfer the address of the next instruction of the call is pushed in this step. Call conditionally, colon carry, colon no carry, colon positive, colon minus, colon zero, colon no zero, colon parity even, colon parity odd. These are just with call with conditions. Means if the carry is one, carry flag is one means if there is a carry or there is a borrow. Okay, borrow means you know that. Call on no carry means the function or not a function. It is also called subroutine. Yep, subroutine. So we can say that what I'm trying to say. Listen carefully, my friend. Listen carefully. In C language, functions. They are functions. Okay. But in 8085, the function are called subroutine. Okay. We can say that functions are called subroutines. Means this is in 8085 या फिर दिस इज इन असेंबली लैंग्वेज कहते हैं इसे असेंबली लैंग्वेज को फंक्शन को सब रूटीन्स कहते हैं यू नो व्हाट आई एम ट्राइंग टू से because we are studying assembly language here okay we are not studying higher level language we are studying assembly language okay okay so yeah. So I think I made my point clear. हाँ धीरे धीरे ऐड किया okay. So yeah. So I think I made my point clear. I think I can do programming. First, I will do some push and pop instruction, and I will finish this stuff. You know, it's hard to learn microprocessor stuff, but I know how to deal with the semester. Okay, I got some ideas to deal with that. Okay, I know how to deal with this semester. I know what are the requirements, what I have to study basically. Okay, till this point I don't know, but from previous exam, I know I understand the feeling what I will write in the papers. Okay, what subject I will focus on. Okay, we'll see that. Okay, so yeah, what I'm saying that you can clearly say by grammatical mistakes, uh, but I know it. Okay, uh, but if you want to speak, just speak whatever you speak. Uh, I know grammar plays a role, but just speak, yeah, just speak. uh, Improve your grammar. Actually, I don't have enough time to learn basic grammar again because I have so less semester schedule. Okay, there's so hectic schedule, so that's why I'm not able to study grammar's basics. So what I'm trying to do is that ki just I'm just speaking whatever goes in my mind, whatever going through my mind, I just speak. Okay, I don't care about audience, I don't care what people think about me, I don't care if people said, oh, he's talking to himself, so he is a mad person. You can say I'm mad. Okay, I really never don't care because if something is helping in my career, okay, so I will do that. I will definitely do that. Okay, so yeah. These teams basically playing a vital role in my productivity. So I will continue this series as long as I can. Okay, so I'm telling you this. Okay, so coming to the instruction, I will let you know what instruction I read. Just I'm just writing. I'm just watching pushing a video again. Not again means that's my fifth video, which was remaining of from Bharatacharya Academy. You know, he's a great teacher. I never saw a teacher which put so much efforts to his teaching. Okay, yeah, yeah. It's good to know. Speaking comes by speaking, my friend. If you don't speak, you will be hesitated. You know, if I want to some ask some doubts from ma'am or sir. Okay, so I'm just talk to them throughout English, which I wasn't able to speak that before. Okay, so yeah, the difference is clear. And I know that There is no person who is there to correct my grammar, but speaking comes by speaking, my friend. That's all what I want to say. That okay. So coming to तू चली जा तू चली जा पर भूलना कि मैं हूँ बस तेरा
Hello people, I'm Bharat Acharya. Welcome to a new video. So in today's video we're going to learn the last group of instructions of ADD5 that's called stack, IO and machine control. Okay, so this group has instructions related, as the name suggests, it has instructions related to the stack, which primarily are push and pop instructions. They come independently as a 5-mark question, explain stack operations for ADD5. Also push and pop are required to learn call. That's the reason why I'm doing this group before doing the branch group. Okay, because call instruction needs a push, return needs a pop. So you first need to understand these instructions. Then IO. In IO you learn in and out instructions. So far you've been working with instructions which work on memory. The whole instruction set works on memory. Only 2 instructions out of the instruction set work on IO devices. They are called in and out instructions. So I'll be teaching you those. What's the concept of IO addresses, etc. And then finally, in machine control, you got instructions like sim, rim, EI, DI, NOP, and halt. Okay. Now all of these instructions we're going to cover. Okay. So the first instruction of this group is the stack part of group. So it's called push. So you'll be learning push and pop instructions. Now when you write push, your intention is to put something into the stack. I'm sure you know, you've seen the architecture video, so you know what the stack is. Stack is a part of the memory where it can be present anywhere in the memory. Where is it present? It's given by the stack pointer. Stack pointer is a register. We can initialize it there.
I'm so lonely if I can't.
Any number and decide that my stack should start from so and so location. Okay. Now here. So when you do a push, you're putting some data into the stack. You have lots of data with you. You need it. not now but later. So you go on pushing it into the stack. So the method. Okay. So the first instruction of this group is the stack part of group. So it's called push. So you'll be learning push and pop instructions. Now when you write push, your intention is to put something into the stack. I'm sure you know, you've seen the architecture video, so you know what the stack is. Stack is a part of the memory where it can be present anywhere in the memory. Where is it present? It's given by the stack pointer. Stack pointer is a register. We can initialize it with any number and decide that my stack should start from so and so location. Okay. Now here, so when you do a push, you're putting some data into the stack. You have lots of data with you. You need it not now but later. So you go on pushing it into the stack. So it's free. Your registers are free. Whenever you want, you can get back the data. Okay. Now to put data in the stack, you use a push instruction. To get the data back, you use a pop. Now when you do a push, you cannot write a number. Push and pop do not support immediate addressing mode. You know what is immediate addressing mode? Writing the data in the instruction is not allowed in push and pop. They only work in register addressing mode. That means the only thing that can be written over here is a register. Are you clear? Further, the register has to be a 16-bit register. Intel has this restriction on push and pop operations. They can only be 16-bit operations, and there is a very good reason for it, but not right now. When you do interrupts, I'll tell you what is the reason why stack operations are compulsory. 16-bit operation, but there's a good reason for it. Okay, so you cannot push an individual register. You need to push a register pair. So when you write push B, you're pushing BC pair. Students say, sir, you told us whenever there is a pair, there will be an X in the instruction. If you remember addressing modes lecture, I told you, yes, I agree. But that is when there is a confusion whether it's a register or register pair. In push and pop, it is understood that it has to be a register pair. So there is no X required. It could have never been B register individually. Okay. As also you know, but the 2-bit operations, and there is a very good reason for it, but not right now. When you do interrupts, I'll tell you what is the reason why stack operations are compulsorily 16-bit operations, but there's a good reason for it. Okay, so you cannot push an individual register. You need to push a register pair. So when you write push B, you're pushing BC pair. Students say, sir, you told us whenever there is a pair, there will be an X in the instruction. If you remember addressing modes lecture, I told you, yes, I agree. But that is when there is a confusion whether it's a register or register pair. In push and pop, it is understood that it has to be a register pair. So there is no X required. It could have never been B register individually. Okay. As also you know, a register pair is always indicated by its higher byte. So for BC pair, you write B, not C. So there is no instruction like push C or push E. So what can you push? You can write push B for BC pair, D for DE pair, and H for HL pair. Are you clear? So we are writing push B. When I write push B, my intention is to push the value of BC pair into the stack. This is your stack. These are all elements of the stack. This is the top of stack pointed by the stack pointer. Stack pointer gives the address of the top of stack. These are empty locations at the addresses SP-1 and SP-2. Is the picture clear? Now, since BC pair is 16 bits, when it will go into the stack, it will occupy 2 locations. You know these basics of memory. One memory location always carries 1 byte. 1 byte means 8-bit. BC is 16 bits. So it will require 2 locations to be stored into the stack. Are you clear? So when you write push B, you're pushing the value of BC pair into the stack. Now BC pair, when it goes, it will not overwrite on the existing top of stack. It's like SMSs in your SMS folder or WhatsApp messages in your WhatsApp folder. Every new message comes above the previous message. It will not overwrite on the existing message. So it will come above it. So above it means these 2 locations. So now here is the question. Who will go where? Either you by heart it or you understand it. I've told you, the first lecture itself I told you, you'll never have to by heart anything in this subject. In my subject, there is no by hearting because there is logic for everything. In B and C, B is the higher byte. This is a higher byte and lower byte. You understand the concept, right? This is a higher byte, this is a lower byte. SP-1 and SP-2, which is a smaller number. SP minus 2. Correct? What is the rule I have told you?
Lower
byte, lower address. Higher byte, higher address. Remember this rule? Say it again. Lower byte, lower address. Higher byte, higher address. This is the lower byte, it will go to the lower address. This is the higher byte, it will go to the higher address. Is the picture clear? So you will get B over here and C over here. So who will go in first? B. You're not going to put C, then come down and put B. I mean, come on, let's be serious. It's going to go in a sequential manner. So what will go in first? B. Now, where will B go? Pay attention to what I'm saying, okay? This discussion will make you understand the timing diagram of push and pop. Where will B go? Is B going to this address or to SP minus 1? SP minus 1. Who will give that address in the system? SP register. SP is giving this address. If you directly push B, that means it will come over here. You don't want it to come here. You want it to come here, which means before B goes into the stack, the first step that will happen is SP will become SP minus 1. Please tell me, did you understand? This is the first step of the execution of push instruction. SP will become SP minus 1. So if SP was, let's say, 4002, it will become 4001. Should this happen first? Yes, that is SP will become SP minus 1. So if SP was, let's say, 4002, it will become 4001. Should this happen first? Yes, that is how you will get the address 4001. One to put into the stack. See, I am the processor, this is the memory. In the memory, there is a stack. If I, the processor, wants to do operation, there are three buses: address bus, data bus, control bus. On the address bus, I need to put an address. How do I put SP minus 1? The address is given by SP register. If I want to put SP minus 1, I have to first make SP minus 1. Are you understanding my point? SP is a register which is 4002. I don't want to put 4002 because this operation has to happen at 4001, which means the first thing I need to do is make 3 microcontrollers to put into the stack. See, I am the processor, this is the memory. In the memory, there is a stack. If I, the processor, wants to do operation, there are three buses: address bus, data bus, control bus. On the address bus, I need to put an address. How do I put SP minus 1? The address is given by SP register. If I want to put SP minus 1, I have to first make SP minus 1. Are you understanding my point? SP is a register which is 4002. I don't want to put 4002 because this operation has to happen at 4001, which means the first thing I need to do is make SP 4001 so that it gives me a fresh address to do my push. Please tell me, did you understand this? So the first thing that will happen is SP will become SP minus 1. Now it's pointing to a blank location. Here you will put the data of B register. Then again SP will become SP minus 2, and here you will put the data of C register. So to write it as steps, SP will become SP minus 1, and
I qualified. Why I qualified? अबे यार तो ठीक है okay actually I was qualified for round 2. उस पे का गया था So yeah, we will do a break for sure. No, I'm not happy because I qualified. Uh, what I gonna say though? Okay, anyways, we have completed one session now. Ready for second session. Okay. I will eat that portion of the fish.
The new location pointed by SP. This box means at the location pointed by SP. Since I have written SP has already become SP minus 1, that means this is now location SP minus 1. That means it is this location. At this location, we will put the value of B register. Again, SP will become SP minus 1, which effectively means it has become SP minus 2. Correct? Because this is the second time we are decrementing it. At this new location pointed by SP, we are putting the value of C register. This is your push operation. Are you clear? Let's see it on my fingers. This is the topper stack pointed by SP. Let's say this is location 4002. It contains something. I want to push B and C register. First, SP will become SP minus 1. So it will point to a new location. I will put the value of B register over there. Then SP will become SP minus 1 again. I will put the value of C register over there. So by the time the operation is over, SP is now pointing to the new topper stack. Please tell me, are you clear? That was push instruction. What? Was it difficult? Nothing difficult. Come on, this is 8085. It was made in 1970s. Really, you think it's going to be difficult? Yeah. When you say something, when you learn ARM or when you learn Pentium, and then you say, oh yeah, it's a little difficult to understand. I agree. This is all very simple. You just have to learn things the right way and stop by hearting. If your mind doesn't agree with it, that means you're not understood it. Now don't just cover up by hearting it. Read it again and again. You will get it. Come on, it's not really difficult. Next one, pop B. Pop B. Now you're going to answer this by yourself. We will pop the data from the stack and put it into BC pair. I repeat, we'll pop the data from the stack and put it into BC pair. BC pair is how many bits? 16. So it wants 16-bit data. 16-bit data will come from one location or two locations? Two locations. This is the topper stack pointed by SP. So if this address is SP, let's say 4002, this is 4003. You understand that, right? So this is SP plus 1, this is SP plus 2. When I do this pop, this data will come into BC pair. Now, who will get which value? Again, same principle. Lower byte, lower address, higher byte, higher address. This is the lower byte, it will get from the lower address. This is the higher byte, it will get from the higher address. This address is SP, this is SP plus 1, so it's a bigger address. You understand the point? So, C will get the value 34, B will get the value 12. Once these two are popped, SP will become SP plus 2. So, let's understand the sequence now. What is going to happen first? When we did a push, what happened first? First SP got decremented, then we push the data. When we do a pop, what will happen first? Will first SP get incremented? No. Did you get that by yourself? If you got it by yourself, great. Because that means you're now interested in learning the subject properly and not by hearting it. You're not waiting for it to finish. You want to learn it. How can you change SP? If you change SP, you'll never be able to access that location. That location, the address was given by SP. First, you will pick up data from that location. So first 34 will go into C, then SP will become SP plus 1, then 12 will go into B, then SP will become SP plus 1 again, which means SP plus 2. Please tell me, did you understand? So what's your first step? First C will get the data pointed by SP. SP will then become SP plus 1. B will get the data pointed by SP, which means the new location. And again, SP will become SP plus 1, which effectively means it has become SP plus 2. On my fingertips, come on. This was something, then there was 1, 2, then there was 3, 4. This is the top of stack pointed by SP. You want to pop this data. First, you will pop this data, my index finger data. First, you will pop this data. Then SP will become SP plus 1. Then you will pop this data. Then again, SP become SP plus 1. So SP will now point to the new number. This has been popped out and has been taken into BC pair. Please tell me, did you understand this? Are push and pop clear? Things to remember, push and pop do not allow immediate addressing. You cannot write a number. You can't write push 2000. First put 2000 into a register, then push it. Secondly, it can only work on register pairs. Push and pop are compulsorily 16-bit operations. So what are the pairs that you can push? You can push BC pair, D pair, HL pair. Who's left out? A. The most important register of ADD5 is A. But A doesn't form a pair. That means you cannot push the value of A. How sad. No, nothing to be sad about. They've created a provision for this. If you ever need to push and pop the value of A register, you can make a pair out of A and F. AF, accumulator and flag register. Please focus. Accumulator and flag register together form a 16-bit pair. That is called PSW, Program Status Word. I repeat, in which A is the higher byte and F is the lower byte. Before I say one more thing, get this clear. PSW is only created so that you can push and pop.
Print working active.
PSW is only created so that you can push and pop the value of A register. Are you clear? And of course, flag. My point is, you cannot use PSW as an operand in any other instruction. Have I made myself clear? I'm using simple language. I'm not mixing words. If you use PSW, you can only use it in push and pop instructions. No other instruction can you use PSW as an operand. So it's not some new register pair that you form. It's just what do you say in our Desi language, jugaad. It's a provision to simply push and pop a register. Okay, you cannot use PSW for any other instruction other than push and pop. Okay, don't think you got one more pair to play with. No. Now, when you write push PSW, the operation is same. I've just now explained to you push. Now I want an answer from you. A and F have to go into the stack. A is the higher byte, F is the lower byte. What's the first step? Correct. First, SP will become SP minus 1. We will put the value of A. SP will again become SP minus 1. We will put the value of F. Would you want me to write the steps again? What's the point? It will be the same steps. SP will become SP minus. Just instead of B and C, I'll be writing A and F. It's the same thing. So it's not like a new instruction. It's just that you had to know that there is something called push PSW and similarly pop PSW. You can pop back this value into A and F whenever you.
Okay.
Want to. So when you're doing a pop, first 34 will come into F, SP will become SP plus 1, 12 will come into F, SP will become S. Plus. Did you understand? So that's everything about push PSW and pop PSW. With that, we finished the stack operations of 8085. So in Bombay University, when 8085 used to be there in the syllabus. Now Bombay University engineering degree syllabus doesn't even study 8085. Diploma still does. So there you get this as a 5-mark question. Explain push and pop, or simply explain stack operations of 8085. So explain these two in detail and just mention that there is push PSW and pop PSW also. Okay, you don't need to explain it all over again. It's the same instruction. Now, the next part, I/O. We finished the stack part, now we're looking at I/O. I/O stands for input output. Now you know from this basic diagram of the subject, there are 3 parts in a computer: MUP, memory, and I/O. MUP is your processor. You can transfer data either between MUP and memory or between MUP and I/O. Out of 74 instructions of 8085, the whole instruction set, there are only 2 instructions that transfer data between MUP and I/O. Everything else works between MUP and memory, like the simplest example that we saw over here. Push, what are you doing? Transferring from a register to the memory. Registers are in the MUP. That means push goes like this, pop goes like this, etc. All the instructions that we've learned. But I/O instructions, in and out, are the instructions that transfer data between these two. This is obviously in instruction. Come on, even if I didn't tell you, you would have realized that. And this is out. So in does an input, out does an output. Now, when you do in or out, the data can only be transferred via a register. Compulsory. In 8085, in and out. In 8086, just different forms of a register. But this rule is there for most of the Intel processors. In and out instructions, the data will be transferred only using a register. Are you clear? So when you write in, the data comes into A. When you write out, the data goes out from A. Are you clear? Keep looking. Now, here I have shown only one box of I/O. Will there be only one I/O device? No. How can there be? There will be many I/O devices. So the real picture looks like this. This is the MUP. These are several I/O devices. I'm sure you identified them: keyboard, mouse, printer, monitor, and so on. Keyboard and mouse are input, printer, monitor are output. They are all connected to the MUP. Whatever data will be transferred through a register. So when I do an in, data comes into A. When I do an out, data goes out from A. So I'm sure by now you understood there is a problem. When I do an out, data will go out from A. Should it go to all devices or one device? Obviously only one device. Whatever you send to the monitor, should it also go to the printer? No way. I'm sure you understand that, right? The paper will be wasted. That's all I'm saying. I don't know what you're thinking. But my point is, focus. So my point is, when you do out, data should go to one device. When you do in, data should come from one device. That means, though there are lots of I/O devices, you're working with one at a time. Students say, sir, I'm listening to music, I'm watching a movie, so that means I'm watching the movie also and listening to music also. Yes, but in one cycle, only one data goes to one device. Processors work crazy fast. The modern processor works at 3 gigahertz. It can do 3 billion operations in a second. So it will send data to memory I/O processor, to monitor and speaker, and monitor and speaker, and monitor speaker so fast that you will think that it's doing both simultaneously. Come on, 3 billion operations per second. You understand what is the speed of a processor today. Anyway. So in one operation, you're dealing with one device. Just like it's the same idea. Look at this memory. 64 KB is the memory of 8085. Are you working on the whole memory in one operation? No. In one operation, you're working on one location. That's it. How do you identify every memory location? By its address. So here, I'm introducing something brand new in the subject. Till now, whenever we said addresses, we were speaking about memory addresses. Till now, you thought only memory had addresses. Now you understand there's another set of addresses called I/O addresses. Memory addresses are called locations. We say location 4000, 6000, etc. I/O addresses are called ports. P-O-R-T-S, ports. Okay, port addresses. I'm sure you know in your computer, on the sides, on the back side, etc. there are various ports. Keyboard port, printer port, monitor port, etc. So all these ports have their own addresses. Are you clear? To the layman, they are ports. To a MUP student, they are all addresses. Each of them has an address. So these are called I/O addresses. These are memory addresses. Now let's take a look at the addresses. Memory addresses go from 0000 to FFFF. What does that mean? They are 16-bit addresses. Because they are 16-bit, you get a range of 2 raised to 16, that is 64K, that is 65,536 memory addresses. You tell me, should IO addresses be such big addresses or smaller? Obviously smaller. Come on, really you have to think about it. Are you going to connect 65,000 IO devices to a computer? Certainly not. Then why have such big addresses? Like in a class of 100 students, we keep roll numbers as 1 million, 2 million, 5 million, be happy. No, if your requirement is less, you use smaller numbers. It just makes it convenient for everybody. So here Intel also did the same thing. It allotted memory addresses as 16-bit addresses, but IO addresses as 8-bit addresses going from 00 to FF. Since they are 8-bit addresses, you get a range of 2 raised to 8, that is 256 IO addresses. So if every IO device is allotted a unique address, you can still connect 256 IO devices. You certainly don't need even that much, but they just came down to 8-bit. From 16-bit they came down to 8-bit. Keeping it 4-bit would be of no use. It would still take up a whole byte space to write. So why not just use 8 bits? So that's why IO addresses are 8 bits. So IO addresses. So here Intel also did the same thing. It allotted memory addresses as 16-bit addresses, but IO addresses as 8-bit addresses going from 00 to FF. Since they are 8-bit addresses, you get a range of 2 raised to 8, that is 256 IO addresses. So if every IO device is allotted a unique address, you can still connect 256 IO devices. You certainly don't need even that much, but they just came down to 8-bit. From 16-bit they came down to 8-bit. Keeping it 4-bit would be of no use. It would still take up a whole byte space to write. So why not just use 8 bits? So that's why IO addresses are 8 bits. So IO addresses are something like 40, 60, 70, 80, etc. Are you clear? Not 8,000, 80. Memory addresses are like 4,000, 6,000, 7,000. This is 40, 60, 80. You understand the difference? Memory addresses are 16 bits, IO addresses are 8 bits. Now, let's look at our instructions. Instructions are super simple. In and out. The syntax is next to in you write an IO address, next to out also you write an IO address. Simple. So in 40, when you write in 40, in means you're getting data. Into which register? A. Only A. What are you getting? 40 or contents of 40? Contents of 40. 40 is some data or address? Address. Are you clear? 40 is an address. Don't look at this I. That MVI as I is different. That is immediate. This is in. Are you understanding that? So in 40. 40 is an address. You're getting the data from IO address 40. Whatever is the data will come into A register. Are you clear? Similarly, out 80. Out 80 means you're sending data from A register to the IO device whose address is 80. So look at this diagram. What does that mean? In 40, you will take the data from the keyboard. Out 80 means you will send it to the monitor. So if you want to take, that's what a computer does. It takes whatever key you press and sends it to the monitor. So it will take from the keyboard, send it to the monitor, and so on. If I tell you take one data from the keyboard, let's do a program, small little program. Take one data from the keyboard, take another data from the keyboard, add the two and display the result on the monitor. In 40, the first data comes in A register. Move it to some other register like B. Move B, A. That data is now safe in B register. Now again do in 40. The second data has come in A register. Add B. The answer has come in A register. Display it on the monitor. Out 80. Tell me, did you understand this? In case you could not catch up on this, it's okay. It's okay. Everybody doesn't learn together. All 5 fingers are not the same. Programming is a skill. It's like riding a bike. It's like swimming. Some people get it instantly, some people take time. But who gets it? The ones who keep trying it. You don't try it, you'll stay where you are. Finish your whole life without knowing how to swim. Come on, why do you want to do that? Try it. It's a skill. Sometimes programming is a skill. You don't want to spend your whole life and get a tag of an engineer without, and in the background, no, I've made a fool of everybody. I don't even know how to program. Come on, is that kind of an engineer that what you want to be? Programming takes time to understand. Some people get it very fast, some people take time. But eventually, if you keep going at it, you will get it. It's easier than swimming and it's easier than cycling, honestly. Okay, you just have to be useful. You get used to your registers. I'll just repeat this. In 40, the first number came in A. You transferred it into B. In 40, the second number came in A. Now you added the two numbers. Answer is in A. Out 80, you send it to the monitor. We will be doing extensive videos on programming. Okay, right now I'm teaching you the instructions. This is just something that just came randomly in my mind, so I thought I'll just do it with you. I'll keep it on the board in case you want it. So that finishes your in and out instructions. Lastly, machine control instructions. Uh, SIM and RIM stands for set interrupt mask and read interrupt mask. I will be teaching these instructions in detail. They are 10 mark questions, okay? I'll be teaching them in detail, not now, 2 lectures later when I do interrupts. I would love to teach it right now. I'm anyways going to teach you 2 lectures from now. I'd love to teach it right now. You don't know what it is for me to hold back that information, how much effort I'm putting right now to control myself. But it is better for you. To understand SIM and RIM properly, you first need to understand the whole interrupt structure. Right now, no matter what I say and I put all my energy into it, you will not be able to understand it as well as you would once you finish learning interrupts. So just be patient. 2 more lectures from now, when you learn interrupts, you'll understand in that topic. Again, these instructions will come and you'll understand them in detail. If you still want to know, if it's like tomorrow is your exam, you just want to know what SIM and RIM are. SIM is used to individually mask interrupts. Mask means disable, and RIM is used to read which interrupts you have masked. In case you masked them 10 times and now you've forgotten which one you masked, you can do a RIM and read it back. That's how the name's set interrupt mask, that is used to set the masking pattern, and read interrupt mask to read back what you had given. Okay, as of now I'll only tell this much. When we discuss interrupts, you'll be learning SIM and RIM in full detail. Next, EI and DI, they are also related to interrupts, but they are too easy. Even a child will understand them. The name itself is the answer. I don't need to speak one more word. Enable interrupts, disable interrupts. As simple as that. EI means enable interrupts. If you write EI, interrupts will work. Interrupts are useful. In the architecture lecture, I've spent good 10 minutes on interrupts. They are useful. So if you write EI, you have enabled them. If you write DI, done. Interrupts are disabled. Now, even if an interrupt occurs, it will not be serviced. Okay, there are some interrupts that can be enabled, some and disabled. Some interrupts are permanently enabled. More about that in the topic of interrupts. But in general, to enable interrupts, you write DI. To disable interrupts, you write DI. NOP, no operation. It does. Does nothing. Students say if it does nothing, then why do we have this instruction? To create a delay. Listen carefully. One of the best instructions to use when you want to create a delay. You've done an operation over here, you've done an operation over here. Between the two, you want to waste some time of the processor. You want to keep the processor busy doing something. You write NOP. What is NOP? No operation. Students say, sir, if it is no operation, then how does it waste time? Good question. First, MUP will fetch this instruction. Then it will decode the instruction. Then it will realize that it has to do nothing. But time was wasted in fetching and decoding instruction. That's it. That's your waste of time. When you do timing diagrams, you come to know this is one opcode fetch of 4 T states. So what you spent is 4 T states. Now put this in a loop with the appropriate count that you want to give, and you can produce whatever delay you want. Are you clear? You can also produce delays by other methods. If you don't like NOP, no problem. Do increment B, decrement B. Tell me, increment B, decrement B. What have you managed to do? Nothing. If B was 25, become 26, then again become 25. So at the end of the day, you've done nothing, but you wasted time. Correct? So you can produce a delay like that also. Add B, subtract B. Now you get the drift. Push B, pop B, and there's so many things. All of them will affect some or the other register and will also indirectly affect flags. NOP does not touch any register but still gives you a delay. That's what I say. It's the safest, cleanest way of producing a delay. But it's not the only way. Programming, the beauty of programming is 10 people write programs in 10 different ways. So other programmers, some programmers use some of the instructions. There's nothing wrong with that. You can do that as long as you're careful about what registers you've changed and what is the effect on the flags. As long as you're careful about that, that's good. If you don't want to think of all this, use NOP. It's the safest instruction to produce a delay. Is there in every processor doing exactly the same thing? Nothing. It does nothing. Just produces a delay. The last instruction, come on, I don't need to teach you, halt is used to stop the program. When you write halt, the processor goes into a state called halt state, where it stops working. Are you listening? Then after this, you have to restart the processor. That's why many college teachers don't allow you to write halt at the end of a program, because if you write halt, you have stopped the processor. Then what will happen? You'll have to restart it. So if the programmer examiner wants to check the result, he or she cannot check it, because when you restart it, all the registers will lose their values. But if you want to, in reality, stop the processor from working, write halt, it stops the processor. What does it do? I'm just giving you processor level, teacher level knowledge. You don't need it as a student, but just there in my mind, so I'm just telling you. There is a flip-flop inside the processor called halt flip-flop. It makes that flip-flop 1. This instruction is over. When the processor starts the next instruction, the first T state, it checks the halt flip-flop, it sees it's 1 and stops working. So the time required to do this instruction is 1 opcode fetch of 4 T states, but the time required for the MUPI to stop is after this 1 T state to check the halt flip-flop. I just gave you information at teacher level. You don't need it as a student. As a student, halt is the simplest instruction. It will stop the processor from working. Now it is done. It is over. You have to restart the processor to start it all over again. That's it. That was the whole last group of instructions. So in all of these instructions, the only instruction I have not explained to you deliberately is rem and sim. You don't know how much it is affecting me that I'm not explaining them, but it's in your benefit. You will understand rem and sim when you understand interrupts. Otherwise, you will get half knowledge, which is very dangerous. So just wait for 2 lectures. When I do interrupts, you'll understand what rem and sim are. Other than that, we finished push and pop, in and out. Sim rim, okay, I just told you what they are: EIDA, NOP, and halt. That was the whole stack IO and machine control group. I hope you enjoyed learning. Wish you all the best. Do well.
तू चली जा पर भूलना कि मैं हूँ मेरा पैगाम।
Hello people, I'm Bharat Acharya. Welcome to a new video. So in today's video we're going to learn 8085 programming. I'm going to teach you basics of programming and then we're going to take it to a higher level. We'll start with a simple program first to add two numbers. We'll do it in the most simple way, using LDA and STA instructions. These are the instructions people who start programming use. Okay, they're the most basic way of doing a program. Finish that. In that program, of course, we're going to take care of carry. So I'm going to teach you how to handle. Now, carry is not some one program. If you know how most first to add two numbers, we'll do it in the most simple way, using LDA and STA instructions. These are the instructions people who start programming use. Okay? Basic way of doing a program. Then, after we program, of course, we're going to take care of carry also. So I'm going to teach you how to handle carry. Now, carry is not something that happens in one program. If you know how to handle carry, you'll be able to do it in various programs because that situation arises across 40 to 50% programs that you do. Then, I'm going to teach you the same program of add two numbers, but how to do it in a professional way. College exam, you do it, it's either of the two ways you'll get full marks. But your life doesn't end with adding two numbers. You want to do serious programming. Now, when you want to do serious programming, you want to start using M, the memory pointer. That's the strongest tool of 8085 programming. So I'm going to teach you with this example of adding two numbers, how to do the program using M. Once you know that, you'll be able to do big programs which involve major loops because in those programs, M becomes your best asset. Anyway, after that, we're going to take it a level higher. I'm going to do block transfer programs. These are regularly asked questions. So first we're going to see a normal block transfer, transferring a block of data from one place to the other. Why does this program keep coming a lot? Because where is it used? It is used in copy paste. Now copy paste is something that we do every day. So when you're doing it next time, you copy a set of data, control C, control V, or command C, command V if you're using Mac. When you do that, you should strike your mind that I know how to write the program for doing it. So I'm going to anyways teach you a normal block transfer. Then I'm going to teach you inverted block transfer. Block of data containing 1, 2, 3, 4, 5. When it's inverted, it should be 5, 4, 3, 2, 1. So it's also called infix, postfix, or string reversal, whichever way. Different universities call it different way. But basically, it's an inverted block transfer. Then I'm going to show you how to exchange two blocks. This is a whole block of data. This is another block of data. By the time the program is over, this should be here. This should be here. So that's what this video is going to be all about. Okay. So our first program is to add two numbers. So this is how the question will be there in the exam. Write a program to add two numbers. Either they will give the addresses or you assume. So let's say the numbers are stored at in the memory at the location 2000 and 2001. Now both of them contain 8-bit numbers. You tell me, when you add two 8-bit numbers, answer is how many bits? Exactly, 8 bits. Like when you write add B, operation is A plus B, the result comes in A. So answer is 8-bit, no doubt. That is called the sum. And there is a possibility of a carry. Now what are the possible values of carries? 0 or 1. You get this clear? Carry can never be 2. 9 plus 9 cannot be 20. 99 plus 99 cannot be 200. Similarly, in hexadecimal system, both these numbers are 8-bit numbers. So worst case situation, there will be FF. FF plus FF is 1FE. Like 99 plus 99 is 198. Similarly, FF plus FF is 1FE. In 1FE, FE is the sum, 1 is the carry. So basically, carry can only be a 0 or a 1. So you got to store both sum and carry. So they will be requiring two locations, 8-bit for the sum, and though carry is 0 or 1 will be stored as a separate location. So we'll be storing sum at 2002 and carry at 2003. Now here is another thing to understand. If they don't tell you where to store the sum and carry, please store it correctly. There is a rule followed always. Lower byte, lower address, higher byte, higher address. Say this again please. Lower byte, lower address, higher byte, higher address. Now 2000 and 2002 and 2003. This is the lower address, this is the higher address. So here the lower byte should come, here the higher byte should come. Now between sum and carry, which is higher? The carry, of course. Why? Carry comes after the MSB of the sum. So it is the higher byte. Like for example, 9 plus 4 is 13. 13 means 3 and a carry 1. Now 3 is in the units place, 1 is in the tens place. So it is more significant. So it is called the higher byte. Are you clear? So we will store the carry over here as the higher address, the higher byte at the higher address. lower byte at the lower address. Now, what's the procedure? As I said, I'm going to do the program in the simplest way possible. Now, I have an advice, okay? Right now, just disconnect from everything else that you're doing and focus here, especially if you have never written 8085 programs, okay? Once you understand one program completely, it will give you massive confidence to understand more programs. And you never learn programs, you learn programming. I'll be teaching you a lot of skills over here, which only if you're fully concentrating, you'll understand every word I'm talking. Okay? So please pay attention and disconnect from everybody else. Now, you want to add these two numbers. Obviously, to add them, first of all, you need to take them into registers. So what are you going to do? Take the first number into some register. So here is your first question. You'll take it in which register? Tell me. There are 7 registers, A, B, C, D, E, H, L. You'll take this number in which register? Yeah, A. Why will you take it in A? Because the instruction to do this is called LDA. Get this clear, my friend. There is no LDB or LDC. So what is the first thing you understood from here? Whenever you want to take data from the memory, the register in which you will get the data is A. The gateway into MUP is A. Once the data comes in A, you can transfer into any other register. But it will come in A. Are you clear? So take the first data in A. Now, immediately transfer it into some other register like B. Why? Because you're going to take the second data also in which register? A. Exactly. So when you take the second data in A, you don't lose the first one. So take the first number in A, transfer it into B, take the second number in A. Will you be able to do instructions for doing this much? Good. Now, add these two numbers. Add B, so it will do A plus B. The result will come in A. What is there in A? The sum, which we're going to store at 2002. At 2003, we're going to store the carry. Assume the carry is in C register. We will get it, of course. Now, assume the carry is in C register. We'll store the sum from A to 2002 and the carry from C to 2003. So now the only thing left in our mind is how to get the carry in C register. That I'll teach you as we do the program. First, let's do the instructions for doing this much. Come on. LDA. Get the data of 2000 into A. LDA. Come on, give me the instruction.
LDA
2000 H. Please tell me, did you understand?
Yes, sir.
So A gets the data from 2000.
And MOV A comma B. Move B. MOV B comma A.
Transfer the data into B. Move
B comma A.
B comma A. Exactly. Was it move A comma B or B comma A?
A to B. A to B. Yes.
I always tell this in the class. See, right now I can't see you, but you got to follow this if you want to learn properly. Yes, sir. Say instructions. There's a big difference between thinking of them and saying them. When you think of them, you're 50-50 about what you're going to say. When you say, you commit.
When you say, you commit.
Either you'll end up being right or wrong. If you're right, great. If you're wrong, great. Because now you know what is wrong, so you will not make the mistake again. So much better than just thinking of it is saying instructions. Okay, it's going to help you. Okay, so you took the first number in, transfer into B.
Yes,
take the second number in A. Come on, give me the instruction. Second number in A. Good. LDA 2001. Now you take in your two numbers in A and B. Now add A and B. Come on.
Add B.
Add B. Exactly. Now when you did this, who has what? A has
A plus B.
The sum is in A. Store the sum at 2002.
STA 2002.
STA 2002. Please tell me, did you understand?
Yes, sir.
We have stored the sum in 2002. Assume the carry is in B. I will put it. Can you see I have left space? I'll put it. First, let's just store the carry. Assume the carry is in C register. The carry is in C. From C, you're going to store it at 2003. How are you going to do it? From A, you store it at 2002 by writing STA 2002. From C, you store it at 2003 by writing STC 2003. No, there is no such instruction. There is an STC, but that is set the carry flag. That is not store C register. So what did you understand? If you want to transfer from C register to a memory location, you have to first get it into A register. Exactly. What did I say? I am the MUPI, you are the memory. Between the two of us, there is A register. I want data from memory, it has to come into A. From A, it will go wherever you want. Similarly, if I want to send data to memory, I have to put the data in A and write STA. There is no STB or STC or STD. Are you understanding what I'm saying?
Yes, sir.
So, from C, first take the data in A. Now, come on, give me the correct instruction.
From C, move A, C.
You want to transfer the value from C register to A register. Come on, come on, come on, come on. Move A, comma C. You always write the destination first. It's destination, comma source. So you'll transfer from C to A. Now from A, you'll store it at 2003. STA 2003. Done. End the program by writing halt or return or RST1, whatever your college teacher writes. There are different ways of ending the program. Most common is halt, so I'm writing halt. So now the only thing left to be done is get the correct value of carry into C register. Now who has the carry? The moment we do this addition, carry comes into the carry flag. So what we need to do is, from the carry flag, get the carry into C register. I repeat, from the carry flag, get the carry into C register. Did you understand this? From carry flag, get into C. Now can you write move C, comma carry flag? No, that is not possible. There is no such instruction. So here you need to use some logic. If carry flag is 1, make C register 1. If carry flag is 0, make C register 0. Did you understand this? We've already done the code for storing C register at 2003. Our job is just to get the correct carry into C register. So I say again,
We have completed. We're gonna do 3 sessions today, okay? Because I have to go somewhere. Means that doesn't mean. So yeah, we will do 3 sessions for sure. Let us do it. I don't think I need a break. Let's do it, baby. Shh, shh, shh.
If carry flag is 1, make C register 1. If carry flag is 0, make C register 0. Now, C register can have only two final values, 0 or 1. Don't try to find out both values. That is stupid programming. We say this, when you see somebody's code, you come to know instantly whether that person is serious about programming or is just writing to get it done with. If you know something can have only two values, never try to find both values. Assume one and work on the other. That makes your work half. C register could have only two values, a 0 or a 1. MBIC, 00. I have started my program by assuming that there is no carry. What does this mean? If there is, after this addition, if there is no carry, my program is already working without doing anything. There are only two possibilities. There could be either a carry or no carry. I have assumed no carry. So if there is no carry, I have to do nothing. Please tell me, did you understand? So now I have to handle two cases or one case? Only one case. Which case? If there is a carry. Now, if there is a carry, C register should become 1. To make C register 1, you can write MBIC, 01, or you can write INRC. What do you write? INRC. INC was used in 1886, so you write INRC. Now, when you write INRC, INRC stands for increment C. Now, this line, increment C, should be written only if there is a carry. If there is no carry, I should not do this. So, come here. You initialize C with 0, you took your first number, transferred into B, took the second number, added it. Here, you have to make a decision. If, I'm saying it in English, then I'll write the instruction. If there was a carry, I should do this and continue. If there was no carry, I should jump over this line and continue. Please tell me, did you understand this? If there was a carry, I should do this. If there was no carry, I should jump over it. The instruction is J and C, skip. This is skip.
There is no carry.
J and C stands for jump if no carry. I repeat, jump if no carry. So if there is no carry, directly skip and store the result because you assume C to be 0, it is valid. If there is a carry, it will not jump because I've said jump only if there is no carry. So if there is a carry, it will not jump. Now if it will not jump, what will it do? Will it sit there? If it doesn't jump, it by default it will go to the next location. That means it will make carry 1 and then go ahead. That means bottom line, this instruction will only be executed if the There is a carry. If there is no carry, you will skip this instruction. Please tell me, did you understand this? Yes, is the idea of handling a carry clear? That was the thing I wanted you to learn from this program. Carry is not something that happens only in this program. You will come across the situation of carry in 25, 30, 40, maybe 50% of programs that you do.
बेटे हमको बुला के
After this, in any program, if there is a carry, this is how you're going to deal with it. What's the procedure? Tell me. Take a register like C. By default, initialize it with 0. So you assume that there is no carry. Do whatever you want to do till the part where carry could be produced. Now here you want to check carry. If there is a carry, increment C value. register. If there is no carry, jump over the line where you are incrementing C register. What is this label? Skip. It's a label. You can give it any name you want to. Because I'm skipping an instruction, I've given the name skip. You could have called it down, then you'll writing JNC down. That's just the name of a label, whatever you want to do. You're not skipping because I've written the name skip. You're skipping because of this instruction JNC. JNC stands for jump if no carry. So for the last time, let's just repeat the program, then we go ahead. You've initialized carry as 0. You've taken the first number in A, transferred the number into B. You've taken the second number in A. You have added the two numbers. I think up to here, everybody's okay. Now, at this point, there could be two things. Either there could be a carry or there could be no carry. You assume that there is no carry because you initialize C as 0. So if there is no carry, directly jump and come over here. If there is a carry, make C 1 and then come over here. So by the time you come over here, C register has your actual carry. A has the sum, C has the carry. Store A at 2002, SD at 2002. You want to store C at 2003 but cannot be done directly. So from C first get the number into A, from A store it at 2003. From C get the number into A, from A store the carry at 2003 and end the program called. That was your program. Please tell me, did you understand this? So this was a program to add two numbers. Now, what are we going to do next? Again, a program to add two numbers. Why are we doing it again? This is how a college student will do a program, or a child, a person who has started programming, first day of programming. This is how he or she will write the program. If you ask a professional to do this, which is what you are going to become, which is what you are aspiring to become. Tomorrow you want to be a person who gets paid for writing programs. You want companies to hire you, sit over there, write good programs for them. If you give this program to a professional, they'll have a good laugh over it. You don't do programming like this in the real world. Yes, you start learning programming like this. This is the basic tools. You got the idea to work with registers. If you want to do real serious programming, you have to start using M. M stands for what? Memory pointer. M is the best tool of programming. Whenever you want to access a series of locations, which you need to do for real world programming, you need to use M. There are various programs which can be done only using M. So the sooner you start learning M, the better position you are in when you get into complicated programs. Now, I don't want to introduce M when I'm doing some real crazy logic, because A, you'll be struggling with logic, plus you'll get confused with what M is doing. So a program that you've already done, I'm showing you how to do the same program using M. The moment you'll finish, you'll realize how wonderful this approach is as compared to this approach. Here you are tied up with a lot of...
Let's do programming by myself. पल धीरे धीरे बहकता है। थोड़ा सा कमीना, थोड़ा बेचारा है। इससे इससे आपकी या से उठाओ पर लगाओ। That's my sandwich. ठंडा ठंडा sandwich. That's good. That's good. ठंडा हो गया है। Why it doesn't show? Hello Nikhil sir, are you there? कभी ना कभी तो गर्म होता मेरा लैपटॉप। सैंडविच। तेरा होगा नहीं होगा। Let's take this experiment. You are watching ना? कैसे जुगाड़ करके गर्म करते हैं। गर्म हो जाए बस तो सक्सेसफुल हो। तो ये बहुत ठंडा है सैंडविच। Okay. Okay. Delete this program. Using what instruction? Memory pointer. Oh, that will be Let's wait or not wait. Hot or not hot. It's good. मैं फिर काफ़ी बार बनने की कोशिश करी और प्लेट गर्म हो गई लेकिन सन गर्म हुआ होता है आपको बता दे।
Of rules, here it gives you a lot of flexibility. Anyway, so we are about to start the same question again. Okay, so the exact same question. Write a program to add two numbers, store at 2000, 2001. We will store the sum at 2002 and we will store the carry at 2003. Exact same situation, but now we're going to do it using M. Now, how do you work with M? M is the data of the memory location pointed by HL pair. Say this again. M is the data of the memory location pointed by HL pair. So, if you want to access these memory locations using M, you need to first initialize HL pair. Your first step is make HL pair 2000. How do you do that? LXI H, 2000. LXI-H. What does LXI do? Load immediately. Load immediately into HL pair the value 2000. For HL pair 2000 is data. You put the data 2000 in HL pair. That will now act as an address. Whatever is the number present in HL pair acts as an address whenever you use the word M. So, because HL pair is initialized with 2000, you can refer to this quantity using M. Now, M is this location's data. Is that clear? Now, what can you do with it? Look here. Move A, comma M. By doing this, you have taken this first number into A. Student feels, so what's the big deal? We took the first number in A over here also. Yes, here you can only take the number in A because you can only write LDA. There is no LDB or LDC. But here you can write move B, comma M and get this number in B. You can write move C, comma N and M and get this number in C. Are you immediately understanding because of using M you're getting more flexibility? Of course, this is just the beginning. There is so much more advantage of using M which I'm going to teach you. This just happened in the very first line. So when you write move A, comma M, you have taken the first number in A. Please tell me, did you understand this? So you got your first data. Now, you want the same data or the next data now? Next data. How do you get that? Make HL pair 2001. The moment you make HL pair 2001, this number will be called M. Did you understand this? How do you make HL pair 2001? Come on, come on. LXI-H, 2001. No, my friend. This is so much easier. INXH. You know what is INX? Increment HL pair. When you write INXH, HL pair which was 2000, now HL pair has become 2001. Because HL pair has become 2001, M is now the second location. Please tell me, did you understand this? Now what? The first number is in A, the second number is M. Add them. Instruction. Add M. Did you understand what happened? The semicolon is not required. If you want to write a comment, you write put a semicolon, otherwise it's not required. So when you write add M, you added these two numbers. So what has happened? Here we kept taking numbers into registers and then adding them. Here you are directly adding the value of a memory location. Did you understand what M made you do? You didn't even take the location. You're directly adding that location's data to A register. So does it reduce your steps of programming? Of course it does. This is a much better program than that. And this is a trick that will help you write much complicated programs in a very easy way as compared to using that approach. In fact, there are some programs where you cannot use this approach at all. But here you can do a lot by using M. Let me just finish the program, then I'll teach you more. I'll show you more advantage of using M. Anyway, so when you write add M, these two numbers have been added. Now what? When you added them, the answer has come in A. What does A have? The sum. Now you want to look for the carry. The same trick. Don't look that side, no cheating. How do you handle carry? Come on, tell me. Initialize a register like C with the value 0 right in the beginning of the program. If there is a carry, increment C. If there is no carry, skip that line. Just jump over that line. Remember that or no? Come on, same thing. MVI C, 00. You assume that there is no carry. If there is a carry, I will increment C. If there is no carry, if there is a carry, I will increment C. If there is no carry, I will skip. Jump if no carry to skip. So by the time I have reached skip, who has what? A has the sum, C has the carry. I repeat, A has the sum and C has the carry. So all we need to do is store both of them. How do you store A at 2002, ST at 2002? No, I want to stop using direct addressing mode. I want to do everything using M. HL pair is right now 2001. Just increment HL pair. INXH. HL pair will now become 2002. Please tell me, did you understand this? Now, HL pair is 2002. That means this location is now called M. Store the value from A at this location. How do you store from A to that location? Move M comma A. So you stored your sum. Again, INXH. Again increment HL pair. HL pair now becomes 2003. Store the value of carry at this location by writing move M comma C. Did you see the advantage? You can store carry directly into this memory location. In this previous program, from C first you had to take it into A, and from A you had to store it over here. Now that problem is solved. You are directly storing the value of C register into a memory location. These are the advantages of using M. Program is over, job done, halt. This was the same program using M. This is the same program without using M. Let's see advantages. What's the first advantage you understood? Come on, I'll tell you there are lots of advantages. First advantage, you can only work on A register. Data can only be taken into A or stored from A. Whereas over here, you can transfer data using any register. So it gives you flexibility. You're not over dependent on A for everything. Did you understand? That was the first advantage. Second, let's look at the size of the program. Yeah, on the face of it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, this looks bigger. Oh, no, it is only looking bigger. It is not bigger. See the size of the instruction. I have taught you how to figure out size of an instruction. If an instruction doesn't have a number, it is a 1-byte instruction. If there is a 1-byte number, it's a 2-byte instruction. If there's a 2-byte number, that means a 3-byte instruction, because numbers are never a part of the opcode. They are written separately as operands. I've taught you all of that. So look at the size of this program. This is 2-byte, this is 3-byte, this is 1-byte, this is 3-byte, this is 1-byte. This is an address. You know that, right? This is an address. So 1 and this is 2 bytes. So that means this is 3 bytes. This is 1 byte. This is again 3 byte. This is 1 byte. This is again 3 byte. This is 1 byte. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22. This is a 22 byte program. Compare that to this one. This is 2 byte. This is 3 byte. This is 1 byte. This is 1 byte. This is 1 byte. This is 3 bytes because this is an address. This is 1 byte. This is again 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 1 byte. And this is 1 byte. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This is 17 bytes as compared to 22 bytes. So is this a smaller program? Yes. Does it make a difference? Of course it does. Apps which are smallest in size load the fast, refresh the fastest. The lesser the space you consume, better the programmer you are if you manage to do the same thing in lesser code or lesser number of bytes. So that is it. None of these are really the advantages that I'm talking about. Yes, they are advantages, but real big advantage lies here. This is a program to add the contents of 2000 and 2001, store the sum at 2002 and 2003. Correct? What if I change my question? What if I tell you add the contents of 4000 and 4001 and store the sum at 4002 and 4003? It's the same question, but now since the addresses have changed, you'll have to make changes in your program. How many changes will you have to make? 1, 2, 3, 4. Every possible place you have hard-coded the address. These are rookie mistakes. These are the mistakes where you get errors on websites because people hard code. When you start working in companies, your bosses will hate, your senior programmers will hate it if you hard code numbers anyway. As much as possible, use indirect referencing, not direct numbers, because direct numbers work only on those locations. Indirect referencing is flexible and works everywhere. This is again a program to add 2000, 2001, 2002, 2003. I change the question. Write a program to add the contents of 4000, 4001, 4002, 4003. Same change if I'm doing over here. How many places have I written the address? Only one. This is the only place which I have to change. So what can I do? I can make this a standard function to add contents of two memory locations and pass this number as a parameter to that function. Do you understand what I'm saying? This is how programming is done in the real world. You don't write a program. You know, in your computer there's a program to transfer files. Now, you can transfer thousands of files from thousands of places to other places. For every transfer, there is no separate program. There is one program to do a file transfer. The starting address of the file source, starting address of the destination, the size of the file are sent as parameters to that program. It is one function that does all the operations. This can become a standard function to add any two numbers. Whereas this will add only these two locations per data. If you want to add, if you change the addresses, you'll have to change everywhere in the code. Code is written only once. It is modified again and again. You should write code that can be easily modified. That happens when you use indirect addressing. That is the advantage of using M. I'll give you more advantages. What happens? You added contents of 2000 and 2001. What if I tell you add contents of 2000, 2001 and 2002? Did you hear my question? 2000, 2001 and 2002. That means one more number that you want to add. All you need to do is INXH add M and this carry part. Put this procedure in a loop. First HL pair was 2000, INXH will make it 2001, next time 2002, next time 2003, next time 2004. Putting this much section in a loop will make you add a series of numbers. Nothing of that sort can happen over here. You've written addresses everywhere. If you want to add one more number, you'll have to write that code again, and then for one more number again. Obviously, to add 100 numbers, you don't write the code to add 100 numbers. You write the code to add 2 numbers and put it in a loop. That can only happen over here, not over there. See, don't get scared. I'm not trying to sell this to you. What I'm trying to make you understand is, the more you use indirect addressing, the better you get at programming. Life doesn't end at adding 2 numbers. There is so much more in programming to do, and those complex programs are only possible using M. So I use such a simple program just to make you understand how M works. You know what we'll do? This is what I do in the class. I never thought I'll be doing this in the video when I started, but I just get a feeling, I think doing that over here also will make sense. Let's write this program again. This time I want all inputs from you. Come on, I want you to dictate the program. I do this in the class. I just randomly erase the program, tell everyone to start writing the program and walk around, see what they're doing. What will happen? You'll make mistakes. That's what I want, my friend. Make mistakes, learn from them. Don't be overconfident. Yeah, I know how to do it. And then when you sit in the exam, you can't write more than 2 lines. Make mistakes, learn over here. Come on, dictate.
Oh, fuck.
Once, I'll just give you the logic. Initialize C register as your carry with the value 0. Initialize HL pair with the number 2000. That means this is M. Take the first data in A. Increment HL pair. Second number becomes M. Add these two. Answer is in A. Check for carry. If there is a carry, increment C. If there is no carry, skip. Increment HL pair. Store A over there. Increment HL pair. Store C over there. Please tell me. Did you understand? Come on. Dictate the program. Come on. Don't get scared. Come on. It's easy. It's add 2 numbers. How can it be difficult? Come on. Start. Initialize C. MVI C, 00H. Please tell me, did you understand? Initialize HL pair with the value 2000. LXI H, 2000. Is this much clear? Now, take the data pointed by M into A. Come on. Move A, M. Excellent. Make HL pair go ahead. INXH. It is pointing to the next location. Now, this is M. Add these two. Add M. You added them. Now, check for carry. What's the idea? If there is a carry, increment C. If there is no carry, skip it by writing JNC, skip. This is skip. So when you reach skip, A has the sum, C has the carry. Increment HL pair so that it points to the next location. INXH. HL pair is pointing over here. Store the value of A over there. Move M, A. Again increment HL pair. INXH. Now store the value of carry over there. Move M, C. Job done. Halt. Please tell me, did you understand this? Now, we go into our next program immediately. I'll just move the camera on this side. So, our next question is, write a program to transfer a block of data. Now, these are all block transfer programs. They're very typical.
Okay. So, we have completed 3 sessions. That's our target for today. Okay. We completed successfully 3 sessions. It was wonderful. Sorry, it was wonderful experience to do 3 sessions. And in between these sessions, I also got a news. I was selected for round 2nd in Max Arts. But how? I didn't get it because my test or the quiz were not going good according to me, but somehow I selected round 2nd, and the second round will be tomorrow, 14th of Feb. That is Valentine. Oh, today is Valentine Day. Sorry. It's okay. Let me check if there are any live people. They are no such. So yeah, it's good to have you. We have already touched playbacks of around 20. It's good to have these type of number. So yeah, This is Prasoon signing off from the stage. Be productive, be consistent.